Okay, I want to spend a little time this semester talking about unique factorization in integral domains other than the integers, such as the Gaussian integers or polynomial rings over a field. So let's start with the concept of units, irreducibles, and primes in a more general integral domain. First of all, the concept of divisibility is exactly what we had in the integers. So we say A divides B if B is A times X for some X in your integral domain. So for example, in the Gaussian integers, 1 plus 2i is a divisor of 5, since 1 plus 2i times 1 minus 2i is equal to 5. Or in the polynomial ring, r bracket x, x minus 2 is a divisor of x squared minus 4, since x minus 2 times x plus 2 is x squared minus 4. Okay, next, what is a unit in an integral domain? So start with a ring with unity 1. We'll call an element u a unit if it has a multiplicative inverse. So if there exists some element v where u times v and v times u both equal 1. And again, we'll use the standard notation to write the multiplicative inverse as u to the negative 1 power. So the units in the ordinary integers are just plus or minus 1. These are the only integers whose reciprocal is again an integer. In the Gaussian integers, we again have plus or minus 1, but we also have plus or minus I. Right? The reciprocal of I is negative I, and the reciprocal of negative I is plus I. And then you might ask, well, are there any other units in the Gaussian integers? So if you took a Gaussian integer a plus bi, and you ask what is its reciprocal, well, that's just a minus bi over a squared plus b squared. And so the only way the reciprocal can come out to be a Gaussian integer is you would need the denominator to equal 1. So a squared plus b squared should equal 1. That would imply that a is equal to plus or minus 1. Let's get rid of that. And b is 0. So that would be plus or minus 1 right here. Or a is 0 and b is plus or minus 1. And that would give you these two units right here. In the polynomial ring f bracket x, where f is a field, the only objects that have multiplicative inverses are the non-zero constants, or the non-zero constant polynomials. Any polynomial of positive degree, the reciprocal would be a rational function, not a polynomial. Okay, next let's talk about primes and irreducibles. So in algebra, these words have different meanings. So let D be an integral domain, A be a non-zero element of D. First of all, we'll say an element A is composite if it can be expressed as a product of two non-units. So you can break it up as a product of two kind of smaller objects in some sense. Then we'll say A is irreducible if it is not a unit and not a composite. So that's the type of definition we gave to primes in the integers originally. But in algebra, the word prime is given a different definition. We'll say that the element A is a prime if it's not a unit, and whenever A is a divisor of a product of two things, B times C, then A is a divisor of B, or A is a divisor of C. So this is an actual property of primes in the integers that we had to prove as a theorem. So here we're actually given it as a definition in a more general algebraic sense. So note, first of all, every non-zero element in your integral domain is either a unit, a composite, or an irreducible. So we still have these three categories. Now, what's the relationship between primes and irreducibles? Well, let's first of all look at some examples. So in the ordinary integers, the irreducibles are just the ordinary primes. These are the objects that cannot be expressed as a product of two non-units. But in the algebraic sense, we can throw in the negative primes as well. There's a convention in number theory that whenever we use the word prime, we mean the positive primes. But in algebra, the negatives are considered primes just as well. So this would be, number theorists tend to call these the primes, and in algebra all of these would be called, irreducibles. These would all be called irreducibles right here. And primes in Z are exactly the same objects. So again, they're just plus or minus 2, plus or minus 3. So these two words coincide for the ordinary integers. So what does it mean again to be a prime? It means that, let's take a look. If P is a divisor of B times C, then P divides B, or P divides C. Now that was actually a theorem. We proved a theorem that said if P is a prime in Z, and here I mean a prime in the sense we defined it originally, and P divides AB, then P divides A, or P divides B. And therefore it satisfies the algebraic definition of a prime. Now, why are these the only objects that would be considered primes in the algebraic sense? Well, if you took a composite number like 6, it's a divisor of 2 times 3, but 6 is not a divisor of 2, and 6 is not a divisor of 3, so it would fail to be a prime in the algebraic sense. And likewise, any composite integer would fail to be a prime in the algebraic sense. So the integers, primes, and irreducibles mean the same thing. Unfortunately, that's not true in all domains. Okay, next let's look at the group of units. So if U and V are units in a ring with unity, then I claim the product is again a unit, and the inverse of the product, UV, is just the product of the inverses in the reverse order. So notice I've stated the lemma in a general ring, not assuming it's commutative, and so I need to reverse the order. And this is a familiar result from matrix theory. The proof is straightforward. If you take U times V and you multiply by V inverse U inverse, using the associative law, you just get U times 1 times U inverse, and you end up with 1. And likewise in the reverse order, V inverse UV is also equal to 1. And so the element V inverse U inverse satisfies the definition of a multiplicative inverse of UV, QED. So I claim then that if you're in any ring with unity element, the set of units is a multiplicative group. Well, what does it take to be a multiplicative group? So let's let U be the set of units. First of all, we need U to be closed under multiplication. And why is that? That's our binary operation here. And that follows immediately from the lemma. The lemma says the product of two units is a unit. 2, a group needs to have an identity element. Well, 1 is in the ring. By definition, we say this is a ring with unity, and 1 is a unit. And so 1 is an element of U. And what's the third requirement to be a group? Every element has to have a multiplicative inverse. Well, that's the very definition of a unit. So if U is an element of U, then U inverse is also in U. And so we get a group. Okay, now we were talking about what's the relationship between primes and irreducibles. So we have the following theorem. If you're in any integral domain, primes are irreducible. So primes are always going to be irreducible. And unfortunately, the converse is not true, as we'll see in the next slide. So why is this theorem true? So let's let P be a prime in an integral domain R. I want to prove that it's irreducible. So let's suppose we can factor it. Say P equals U times V for some U, V, and R. I want to prove P is irreducible, so what is my goal here? Our goal is to show that the only way I could factor P is if one of these two objects is a unit. U or V is a unit. Okay, now, what am I given? I'm given P as a prime. So notice this equation tells me that P times 1 is U times V. So that means that P is a divisor of the product UV. Aha! What's the definition of prime? That means P divides U or P divides V. So say without loss of generality, P divides G. P divides U will log. Then Px equals U for some x. And then coming back to this relationship right here, P equals UV, that would imply by substitution, so U is Px, that P is P times xv. Okay, what can I do at this point? Well, we're in an integral domain, and so we have a cancellation law. So I can cancel the P's, and we get 1 equals xv by cancellation. And that tells me that both x and v are units. So in particular, v is a unit. QED, that's what we were aiming for. Okay, so primes are always irreducible, but the converse is false. Irreducibles need not B primes. And for this, you have to construct different types of rings to get counterexamples here. So one example would be to take the ring of integers with the square root of -6 adjoined. So it's like the Gaussian integers, except it's all objects of the form a plus b times the square root of -6, where a and b are integers. And you can observe that this is, in fact, a ring. It's closed under multiplication and addition. So in your homework, you're going to prove the following. 2 is irreducible, but it's not a prime. So 2 is irreducible, meaning you can't factor 2 as a product of two non-units, and yet it doesn't have the defining property of a prime. So indeed, you'll show that 2 is a divisor of the product of these two objects, but it's not a divisor of either one. So we've got an example of an irreducible element that is not a prime. And there's lots of examples of this type. So in general, irreducibles need not be primes. So you can work out the details on this one as a homework problem. Okay, next let's talk about the concept of associates. So two elements in an integral domain are called associates if A is a unit times B, and we'll write A tilde B for two elements that differ by a multiple of a unit of this, like this. Okay, a very elementary lemma says that any divisor of a unit is a unit. So if A is a divisor of U, then A is a unit. Okay, why is this? So A divides U means AX equals U for some X in whatever, we're just working in a integral domain here throughout this section. And I want to prove that A is a unit. Well, U is a unit. So we have some multiplicative inverse V for some V. And now let's just take this equation right here and multiply both sides by V. So AX times V equals U times V, which equals 1. And that tells me that A times XV equals 1, and thus we've got a multiplicative inverse of A. So A is a unit, since XV is an element of R. Okay, so any divisor of a unit is a unit. Okay, finally, one other elementary lemma. If P is an irreducible, then its only divisors are units and associates of P. And that's essentially the definition. Right? To be irreducible means the only way you can break it up as a product U times V is to have either U or V a unit. So you can write that down for an exercise if you like. And property 2 says if P and Q are irreducibles and P is a divisor of Q, then P must be an associate of Q. And that follows immediately from part 1. So if P divides Q, then by part 1, since Q is an irreducible, the only divisors are units and associates. So that would imply that P is a unit or associate of Q by part 1. But by definition, P is not a unit since it's an irreducible. So it must be an associative Q.